Okay, so day, what are we, 3 of this unit, derivatives of exponents. Again, we did, graphs and tables, that was mostly review, but using the pictures. Logs, that's 1 over the argument times the derivative of the argument. Exponents is the new thing for today. So, exponential functions. This is actually an easy one. This one's kind of weird. It's also a transcendental function. Again, just means it's transcendental, not algebraic. You don't really need to know what that means. But let's review, kind of like we did properties of logs before we did log derivatives. Let's do property of exponents before we do exponent derivatives, just to make sure we're okay, and because we can use some of these properties to make our lives a little bit easier. So xy to the m, we can sort of distribute that m, x to the m, y to the m. Wait a minute, I should probably be calling on people for these. Caden, what about that next one? X to the m times x to the n.
X to the m plus n.
Yep. You can add the exponents. James, the nth root of x to the n, how could I write that as 1 power?
Would that be x to the n minus n?
Not to the m minus n. You would that would be, oh, that's not even on here. X to the m over x to the n, that would be x to the m minus n. So that one, I should probably add that one. Do you remember the root power thing? The flower power grows on top and the root grows underneath? Looking at me like I'm crazy, but that's how we figure out what goes where for this. The flower power grows on top, the root grows underneath. So power on top, root underneath. And it helps if you do the hand motions while you're working the problem, right? Flower power on top, root grows underneath. Dylan, how about x to the m raised to the n? What do we do with those exponents when it's a power to a power? Good. Multiply them. X to the mn. I feel like that's an easy one, Jake, but if you don't know it, then you don't know it. What's x to the 0? 1. Anything to the 0 is 1. So that can make our life easy sometimes. Autumn, how about x to the negative 1? What's the negative exponent do? Flips it over, 1 over x. Good. Again, that's all algebra review, but it's important stuff, and we'll continue to use that as we take derivatives. None of that is an exponential function. An exponential function has the variable as the exponent. That's why it's called exponentials, where the variable is. The variable's in the exponent. Like y equals e to the x. And that's another one where you may not remember what the graph looks like. We just said anything to the 0 is 1. E to the first would be e, which is about 2.7. Let's graph what we know here. So 0, 1, 1, comma, 2.7. X is negative 1. We just reviewed that a negative flips it over, so this would be 1 over e, which I don't really know what that is, but it's close to 1 over 2.7. So, I mean, we're just really rounding now on the graph. That's at least in the neighborhood of 1/3. And so if you didn't remember what the graph of e to the x looks like, hopefully those 3 points can refresh your memory. It looks like that. Still no calculus yet. Still reviewing algebra. Limit questions. We can do these. So, Justin, the limit as x goes to negative infinity. So as x heads off to the left, what's our function approaching?
0.
0. Good. And Avery, as x heads off to the right, what's the function doing? Infinity. So that means that y equals e to the x has a horizontal asymptote. You can see it right there, but you can also see it right there, of y equals 0. And then just some comments on the graph. E to the x is never negative because e raised to any power is never negative. The people, or the thing that gets most confusing would be like e to the negative 2. Why is e to the negative 2 not negative? What's e to the negative 2 do? Flips it, puts it in the denominator. So it might be really small, but it's not negative. Okay, well, we want to know what the derivative is. And again, we could do this where we grab a calculator. Instead, I'll just show you on the calculator, because this one is kind of interesting to look at. Let's see. So let's graph. We know what e to the x looks like. E to the x. There's our e to the x graph. Looks really even steeper on that page. Which makes me wonder if I should. Oh, there we go. Let's get a more standard window there. Still looks pretty steep. Now your calculator can do derivatives. This is kind of cool. Second calc. Take a derivative. Whoops, that's not what I wanted. Let's see, where is that? Math. There it is. Again, you don't need to know this yet, but we'll get there. Your calculator can do derivatives. So I want a derivative with respect to x of that first function. And it can do it anywhere you want, right? There's the little bar that means evaluated at. But if I plug in 0 or 1 or 2 there, it's going to give me that one derivative everywhere. I want it to find the derivative for every value of x. So basically I'm asking my calculator now to plot the graph of the derivative of e to the x, because we might recognize what it is. Okay, so there's the graph of e to the x, and now it's graphing the derivative of e to the x. The little thinking bar takes a while doing derivatives because it has to, we'll talk about this later, but it doesn't know calculus. Your calculator finds a numerical derivative every point, so it takes a little while. Okay, so what the heck is going on here? I haven't made a mistake. Let's convince you of what we just saw. Let's turn off the graph of e to the x and only look at the graph of the derivative. So here comes the derivative. Again, it takes a little while because it's got to calculate all those things. Something weird is going on. What does that look like? The same thing. So that means, well, you tell me, what does that mean? What's the derivative of e to the x? E to the x. It's the only function that's like that. Well, I guess 0. The derivative of 0 is 0. So the derivative of e to the x is e to the x.
E to the x. Apologies for interrupting.
Derivative of e to the x is e to the x. Like, oh, what else is there to do? Well, what else there is to do is the chain rule. The derivative of e to the u is e to the u, but then don't forget the chain rule, u prime, or du dx. Okay, well, I don't want to go through all of this to get to the next statement. It's a lot of work. Let's just jump to the end here. if the base isn't e, well, we already know this for derivative of e to the x is e to the x. Derivative of e to the u is e to the u. Chain rule times the derivative of u. The derivative of a to the x is a to the x, but we need to multiply by something else. Based on what we did yesterday and what I said shortly before we started this lesson, any guesses on what we would want to multiply by? How did we fix derivatives of logs when the base wasn't e? Natural log of the base. It's the same fix here. So natural log of a. Except this time we're multiplying by it rather than dividing by it. And then a to the u, so this is going to have lots of things going on. Derivative of a to the u is a to the u. But chain rule times u prime. But our base is an e, so we multiply by natural log of the base. This is another one where there's 4 equations there, but there's really only one equation, and the other 3 are simpler versions of that one. So derivative of e to the x is e to the x, but don't forget the chain rule, and don't forget how to adjust it. And that adjustment, again, that's one that people get backwards. So they know there has to be an adjustment, they forget log versus exponent, which one do you multiply, which one do you divide. But log, the derivative of a log, puts something in the bottom, so you go ahead and put the natural log in the bottom as well. That's the way to remember it. All right, some examples. Find the instantaneous rate of change. Well, again, derivative of this thing at x equals 1/2. So I'll have to plug that in a minute. So dy dx. Hey, these feel weird because it's like, wait a minute, I didn't do anything. The derivative of e to the 4x cubed is e to the 4x cubed. Sort of, right? There's one more piece to that. What else do I need on that? The derivative of the exponent. So that would be 12x squared. So the derivative part is super easy because you don't do anything, but don't forget the chain rule. And we want to evaluate that at 1/2. So that would be, I'm going to put the 12x squared in the front now. 12 times a fourth, e to 4 times an eighth. That would be a safe stop, but that's not allowed. Let me simplify that. 12 divided by 4 is 3. 4 over 8 is 1/2. 3e to the 1/2 is answer choice B. All right. Derivative of e to the x, we know that one already. What's derivative of e to the 2x? 2e to the 2x. And then I can just start picking on people here. So try those next 4. And we'll get some volunteers here to help us out. I think that last one, I think that's a negative x over 2. Same with e, I think that's a negative 2/3 x. The exponent doesn't change. The exponent never changes. Kind of like when you do logs, you don't change the argument of the log. You never change the exponent. Like, leave it the same, and then multiply by its derivative. So Seth, how about e? What's the derivative of e to the 5x? Excuse me, c. What's the derivative of e to the 5x?
5e to the 5x.
5e to the 5x. Yep. Jace, how about the derivative of e to the negative x?
Negative e to the negative x.
Negative e to the negative x. Ashlyn, e to the negative 2/3 x? Yep. And Ambria, e to the negative x over 2? Yep. Don't change the exponent. That would be the temptation here. That's sort of that's the bite the Tootsie Roll Pop or the Blow Pop all at once and crunch it all down. Like, no, one step at a time. Leave the original alone and then multiply by the derivative of the exponent. Number 3, find the slope of the line tangent to the graph. So find the derivative. Oh, what rule are we going to need for this one? Quotient rule. Okay, I'm going to take the time to write this stuff out because quotient rule plus e to the x stuff and putting it all together, I'm not trying to do this all in one spot. So I'll need the derivative of the top, the derivative of the bottom, and then I'll put it all together. Addie, how about the derivative of the top?
I think it's 2e to the
You got it, 2e to the 2x. Jameson, how about the derivative of the bottom? 2e to the 2x. Okay, so now it's ready for the quotient rule. The GF has to come first to make things work out. GF prime, so 2e to the 2x, e to the 2x plus 1, minus, the other way around, 2e to the 2x, e to the 2x minus 1. And I probably don't even have to worry about writing the bottom. I mean, I know it's the bottom squared, but like, look at my answer choices. They all have the bottom squared, so I'm not really worried about that one. Okay, I got to simplify the top here. So 2e to the 2x times 2e to the 2x. I'm not even done with this problem, and I'm going to go ahead and give it the Calculus is Easy, Algebra is Hard problem, or stamp, because I need to know what 2e to the 2x times 2e to the 2x is. Aslan, what's 2e to the 2x times e to the 2x?
2e 4x.
Yeah, 2e to the 4x plus 2e to the 2x minus 2e to the 4x plus 2e to the 2x. Yeah, calculus is easy, algebra is hard. I got a minus sign in there, so I'm thinking something's going to cancel. The 2e to the 4x's will go away. And then the other terms, I can add those and get 4e to the 2x. And we already said our denominator was fine, so that's answer choice A. What rule are we going to need on number 4? Product rule. Why don't you try number? Number 5. What's different about number 5? Doesn't have a base of e. So I know there's going to be a natural log 3 show up. Looking at my answer choices. Is that natural log of 3 going to show up in the top or in the bottom? In the top. It shows up in the bottom when the log is not base e. So I'm pretty sure answer choice B is out. I'm guessing C's probably right, but without the natural log of 3, so C's probably out. Okay, so leave the 3 to the 4x squared alone. And And chain rule would give me an 8x. And then base of 3 means I need a natural log of 3 as part of my answer as well. So, let's see, it's got them in a different order than I wrote them, but there's 8x, natural log 3, yeah, so that's answer A. I don't know, we've got all kinds of rules going on in 6. Outside in, so derivative of natural log is 1 over the argument times the derivative of the argument. Oh, let's pick on some people here. Austin, how about the derivative of e to the 3x?
E to 3x minus, or wait, e to the 3x.
I mean, you're kind of looking ahead to that next one, but don't do that yet. What's the derivative of e to the 3x? E to the 3x isn't wrong, but there's more to it.
Times 3,
Yes. Why the 3? Where did the 3 come from?
the derivative of 3x.
Yeah. Tootsie Roll Pops. Times 3. Then, how about the derivative of x squared? 2x. And so that's our answer, and it's a safe stop, so yeah, we can just leave that as is. I don't think any of that would simplify anyway. Number 7, using a graph. I want the derivative of e to the f times g. Well, that's going to be e to the f times g. And then I need the derivative of f times g, so that would be the product rule, fg prime plus gf prime. And I guess officially I'm supposed to have parentheses x after all of those, but that gets a little annoying to have to write that 6 times, so I'm just leaving it off, knowing that when it comes time to plug in 6, I'll just need to find f of 6 and g of 6 and f of 6 and g prime of 6. So there's f of 6, and there's g of 6. So let's see here. So f of 6 is 1, g of 6 is 6, f of 6 is 1, g prime at 6. So what's g prime at 6? 1/2. Why did you say 1/2? Because that's the slope of g at 6 is 1/2. G of 6 is 6. And then f prime of 6. Johnny, what's f prime at 6?
That would be -1.
Yes, -1. Uh-oh, did I mess something up? Oh, it should be a plus. Yeah, I don't know what yeah. Plus from the product rule, and g is also positive 6. Yes. So that would be a great safe stop answer, but that's not a choice. So e to the 6, that's on all of them. 1/2 minus 6. Let's see, that would be 1/2 minus 12/2 is -11/2. There we go, answer choice D. Alright, so not too bad today, but I feel like this is all of math. What we learned in one particular day is not that bad, but you still have to know all of the things we learned the previous days. And that's definitely true today, as most days in calculus. So today's assignment would be worksheet number 3. Derivatives of exponential functions. And you've got plenty of time to work on that. We got through a lot of popsicle sticks today, so today was a good day. Today is a good day. Yeah, you still got 35 minutes or so.